Welcome to a special topic discussion in Business 12 on Bayes' theorem, a powerful concept of conditional probability that is extremely important in data analytics. First, let me tell you the story of Steve. Steve's a very shy and withdrawn individual. He's invariably helpful, but has very little interest in people or in the world of reality. He's a meek and tidy soul, and he has a need for order and structure, and a passion for detail. Is Steve more likely to be a librarian or a farmer? You most likely are analyzing the description of Steve and trying to estimate the probability that he is either a librarian or a farmer. And if you're like most people, you arrived at the conclusion that he is more likely to be a librarian. And you would be wrong. While the train of thought that brought many people, perhaps including you, to arrive at the conclusion that Steve is a librarian is based in rational thought, it does not take into account other facts, and specifically one other fact, that can affect your estimation. How many librarians versus farmers exist in the population? There are many more farmers than librarians here in the United States. How does that fact affect our estimation of Steve's occupation, if at all? This thought experiment is based on seminal research conducted by Daniel Kahneman and Amos Tversky. In their study, most respondents said that Steve was a librarian, but they, like most people, neglected to include the information about the ratio of librarians to farmers in their judgment. At the time of this research, the ratio of farmers to librarians in the United States was 20 to 1. There were 20 times more farmers than librarians. Recent estimations put the number at 60 to 1, but let's stick to the 21 number here in our discussion for now. Just looking at the population of farmers to librarians, the probability of Steve being a librarian in the general US population is 4.8%. We can arrive at this estimation using the 20 to 1 ratio of farmers to librarians, dividing the number of librarians in this ratio, 1, by the number of librarians and farmers in this ratio, 21. So in general, without any other knowledge about Steve, it's more likely that he's a farmer and not a librarian. So now we know that in general, Steve is more likely to be a farmer and not a librarian. But what about the description of Steve that we obtained earlier? Should that change the probability that Steve is a librarian? Shouldn't additional information about Steve help us to refine our estimate of whether he's a librarian or a farmer? Granted, it's a pretty good bet that Steve is a farmer just based on simple demographic data about the number of farmers to librarians. But can we estimate the impact of the description of Steve on the probability that he is a farmer or a librarian? Let's give it a try. First, let's adjust the sample. Multiply everything by 10. Now we have 10 librarians to 200 farmers. Let's then apply some estimations about the description of Steve as a shy and helpful individual, also including all of the other traits mentioned in that description. Let's say we're able to determine that 40% of librarians and 10% of farmers fit this description. With this information, we can now calculate the probability that Steve is a librarian given this new description. This is a simple ratio of the number of librarians who fit the description, 4, divided by the total number of librarians and farmers who also fit that description, 24. This gives us a probability of 16.7%. So the impact of the description increases our estimation of Steve being a librarian from 4.8% to 16.7%. The probability calculation of Steve being a librarian is an example of Bayes' theorem in action. Bayes' theorem is a concept in statistics for determining conditional probability, or the probability of the occurrence of an event, such as Steve being a librarian, given a piece of evidence, such as the description of Steve. This concept is attributed to Thomas Bayes, a famous 18th century British mathematician, and the concept is fundamental to the work performed in data analytics. So when do you use Bayes' theorem? Bayes' theorem applies whenever you have a hypothesis, such as Steve is a librarian, you are presented with evidence, such as Steve is shy and helpful, and you wish to obtain conditional probability of that hypothesis. Is Steve a librarian, given that I know that Steve is shy and helpful? Here is Bayes' theorem as it applies to Steve. I'll go through each component one by one. First, the quantity on the left of the equal sign is what Bayes' theorem calculates. The conditional probability of H given E, or the probability that a hypothesis is true given a piece of evidence. In this case, the hypothesis is that Steve is a librarian. The evidence is that he is a shy and helpful individual. And we are trying to calculate the probability that Steve is a librarian given that he is shy and helpful. On the right side of the equation, we begin by multiplying two quantities. First, we look at the probability of E given H, or the probability that evidence is perceived that Steve is shy and helpful, given that he is a librarian. Next, we multiply that quantity by the probability of H occurring in general. In this case, the probability of H is the probability that Steve is a librarian in the general population. Finally, we divide the product of these two quantities by the probability of the evidence occurring in the general population. For this example, the probability of E is the probability of a librarian or a farmer being shy and helpful. Let's assign numeric values to the quantities on the right of Bayes' theorem and see what it calculates. For P of E given H, we can recall that 40% of librarians are shy and helpful. The probability of someone being a librarian in the general population is 1 divided by 21, or approximately 4.8%. And the probability of someone in the general population being shy and helpful is 24 divided by 210, or approximately 11.4%. Calculating everything out, we get 16.7%, which is what we calculated earlier. In summary, here is the general formula for Bayes' theorem. You can use it to compute conditional probability of a hypothesis given evidence that is presented. This simple yet powerful concept can help you to make better sense of the world and determine possible outcome with greater accuracy. Once this video is complete, you can practice using Bayes' theorem on examples that I will give you in this week's module. Let's get going and have some fun.